Hey guys, hello everyone. Alright, so I think I'm audible to all of you. Yeah. Okay, so 1 minute. Let me just. Yeah. Okay, so today in this particular session, we are going to discuss electrochemistry. We are going to actually revise concepts from your electrochemistry. So let's try and do some of the questions and some of the topics. Okay, so first of all, I'll go with the formula. Okay, I'll go for important formula and then I'll go for questions. Okay, so both the things will be done in the class. Alright, questions means I'll be doing PYQs basically. So that's how this session is going to be, and yeah, let's try it. So electrochemistry is basically one of most important portion from your physical chemistry part. Okay, it carries around from electrochemistry you'll get around 2 questions. Okay, at least 2 questions in your CSIR-NET exam, and these 2 questions will be your these two will be, one of them will be 2 marker and the other one will be 4 marker, so that means it carries around minimum 6 marks. Okay, so I'll be discussing about that a little later. So yeah, the books which you can follow for this is Physical Chemistry by Atkins, or you can follow a book by Puri Sharma and Pathania. I guess for every physical chemistry student this book is a must. Then for numerical solving, for problem solving, you can follow a book by KL Kapoor. Alright, so these are the things which you can follow to cover up the topics from your electrochemistry. Okay, so let's go for some basic and important formula first of all. So I'll start from very basic. Okay, I'll start from the resistance formula. So you know resistance is equals to R rho L upon A, where R is your resistance rho. Okay, so the formula is R is equals to rho L upon A. R is your resistance, rho is called resistivity. Okay, it's the property of the material by virtue of which it resists flow of current through it. So that is called as resistivity. Resistance is the property that of a material that it like resistance depends upon the length, area and other things, but the resistivity is a material specific term, or is a material specific property. It depends upon different materials. So for aluminum it will have different resistivity, for iron it will have different resistivity, so it goes like that. All right, so the next one is your conductance. So conductance basically is inverse of resistance. Okay, conductance is denoted by G, and this is basically 1 by R. So if you put 1 by R, what you are going to get is 1 by rho A upon L. Okay, this 1 by rho is reverse of resistivity, that is called as conductivity, and that's what is given by kappa. Okay, a new term or a new letter is denoting this 1 by rho, and that is called as kappa. Okay, this is equals to 1 by rho. So your conductance G will be equal to your kappa into A upon L. Okay, this is for some material. If you want to calculate conductivity of a material, that will be given by this expression. Now the important formula is this for solutions. Okay, conductivity is equals to conductance into cell constant. It's a very important term, or a very important relation by which you will at least get a 2-marker question in CSIR-NET. Mostly you will see in many years it has been asked. Conductivity is equals to conductance into cell constant. Okay, the next thing is equivalent conductance. Just like you know the equivalent mass is there, right? In the same way you have equivalent conductance. So equivalent conductance is denoted by this are lambda. Okay, this is a capital lambda written over here. So lambda eq is equals to kappa into 1000 upon C, where C is the concentration, and this has to be expressed in normality. Okay, then only you will get equivalent conductance. Okay, the next thing is your Kohl-Rosch law. Yeah, good evening Gayatri, hi. So the next formula is your Kohl-Rosch law. Kohl-Rosch law tells you, or basically this is applicable for your dilute solutions. It tells, or it relates the molar conductivity and the concentration of the solution, and molar conductivity at infinite dilution. So the Kohl-Rosch law says that if you keep on diluting a solution, its conductivity will increase. Okay, that's what it is. And at infinite dilution, that means if you have diluted the solution up to a very high extent, at that time the conductivity will be highest. Okay, that's what is the basic term, or that's what is the basic fundamental of your Kohl-Rosch law. So Kohl-Rosch law says that lambda m is equals to lambda naught m minus k under root c. So c is the concentration, lambda naught m is the molar conductivity at infinite dilution, and lambda m is molar conductivity. Yeah, here it is not mentioned, but yeah, molar conductivity. Okay, there is one more term called as molar conductivity, and this can easily be denoted by lambda m, and this will be equal to this will again, like lambda m will be written as kappa into 1000 upon concentration should be in molarity. Okay, so here concentration is there, but that should be in molar. You know, concentration can be expressed in molar or normal. Okay, normal. So one is called as molarity, the other one is called as normality. So if you express concentration in terms of normality, that will give you equivalent conductance, and if you express the concentration in terms of molarity, in that term you will get molar conductivity. Okay, the next thing which we will discuss is your conductance ratio. Conductance ratio is denoted by alpha, and that is equals to your conductivity divided by the conductivity at infinite dilution. So whether you have molar conductivity, so it will be lambda m divided by lambda naught m, that means molar conductivity divided by molar conductivity at infinite dilution. And if you are expressing it in terms of equivalent conductance, then alpha is equals to lambda eq divided by lambda naught eq. So equivalent conductance divided by equivalent conductance at infinite dilution. Okay, the next thing is called as Ostwald dilution law. Ostwald dilution law, like it relates your molar conductivity with the dilution or the degree of dissociation or association. Okay, so it's like 1 upon lambda m is equals to 1 upon lambda naught m plus lambda mc upon Ka lambda naught m square. The terms are here same only. Lambda m is your molar conductivity, lambda naught m is molar conductivity at infinite dilution. C is the concentration, Ka is your degree of dissociation. Okay. The next thing is transport number. Transport number tells you, see, in the solution you have cation and anion both, right? So how much electric current or how much current is being transported or is being it's being carried by the ions. So by respective ion, if you are talking about cation, so the transport number of cation will tell you that how much charges does cation are able to move from one place to other, or they are able to carry charges from one place to other. That is called as that is called as transport number of cation, and same goes for anion also. So transport number of anion will tell you that how much charges does anion are able to carry. Okay, so transport number is given by current carried by your cation or anion divided by the total current. Okay, one formula is there regarding your this transport number, that transport number of cation plus transport number of anion should be equal to 1. That's a very well known equation, or that's a very well known relation. We will be using it later on. Okay, next thing is your conductometric titration. There are the conductometric titration is a titration where we plot graph between conductance and the volume of whatever titrant we are adding. Okay, so you know titration, what it is. When you have acid and base titration, that's the basic thing which you might have done. So when you have taken acid solution, you are like putting a little amount of base into it. So a time will come or a concentration will come where your all the acid is going to get neutralized. That point is called as end point, and that's where we say that it is being titrated, or the process is basically titration, but that point is called as end point. Now if you get that end point, that there are many different ways of getting that. Either you can put an internal indicator like phenolphthalein is the one which we have used in class 11th or 12th, I guess, which is colorless in acidic solution, but it turns out pink in the basic solution, right? So that's what we have done. But here we are going to use more adequate method of this conductometric titration, this titration, that is called as conductometric titration. Here what we are going to do, we are going to plot the conductance versus volume of alkali added. Now try to understand this. If you have initially, you don't have, let's say this is the point 0 where you don't have added any alkali to it. Okay, you have just acid into the solution, and let's say you have a strong acid, okay, plus a strong base is the titrant. You are titrating against a strong base. So at 0, here what I am writing, here I am writing volume of base or volume of alkali which you are going to add. So initially it will be 0, so you only have a strong acid in the solution, right? The strong acid will have high conductivity. Why? Because it will have high conductance. Why? Because it has more number of hydrogen ion and they are going to conduct. Now as you have added, let's say 10 ml of strong base, so those 10 ml are going to neutralize 10 ml of acid, or some amount of acid they are going to neutralize. So the conductance is going to decrease at this point, right? You are going to get conductance at somewhere over here. Then let's say you have increased the volume of base, so again further more conductance is going to decrease. Okay, so conductance is decreasing because the acid is getting neutralized by the base, and you don't have much ions for the flow of which are like you don't have much ion which are capable of flowing the electric current. Okay, so that's why your conductance is going to decrease. So 20, after 30 your conductance will decrease more. Let's say this is the point where all your acid has got neutralized. All the acid has got neutralized at this particular point. Now again, if you increase the concentration of base, what will happen? All acid was neutralized at this point. So let me join these points. So you are going to get this line like this, right? So you have got a point where all the acids are neutralized, but here you have added extra base, right? So who is going to conduct now? So here you have extra base, so base is going to conduct now. Okay, so that's why conductance is going to increase up to some certain extent, because you have added base, and this extra base is basically helping you in conductance. So again the conductance will increase at this point also. If you keep on increasing the concentration of base, the conductance will increase now. So this red line which you can see in the graph is because of the base, okay, the conductance because of base, and this green line which is coming down, it's because of the conductance of acid, and this point will be called as your end point. This is the point where the conductance has been happened completely. So this is the first graph for strong acid and strong base. This is how you get the nature of the graph is this. The second one is a strong acid and weak base. So now let's assume that instead of giving strong base, we are giving weak base. So I'm just going to erase this. So what will happen when all the acid is neutralized? Okay, we are going to have weak base. So if all the acid is neutralized, after that if you keep on increasing the base, so weak base does not dissociate that easily, and if weak base does not dissociate, it is not going to conduct also, right? The conductance is going to be low. So this increase which was earlier in the case of a strong base, that you are not going to observe in case of weak base. So in weak base the conductance is not going to increase, and that's why the curve is going to be something like this. Okay, earlier the curve is going to come down because strong acid is getting neutralized by the base, and after reaching the end point your base is going to, like, because the base is not able to dissociate, so that's why it is not able to conduct, and that's why it is not going to increase the conductance. So this point will be your end point. Now it's pretty simple, right? If you take a weak acid and a strong base, so in weak acid and a strong base, this is the curve which you will get, this particular one, okay, the one which is given above. I have drawn it, like I have drawn two of them here, but yeah, this is what it is. So weak acid, again initially it is not going to dissociate much. After some time when the strong base comes, it is going to give more dissociation of that, and at the end when all the acid is going to get neutralized, at this point your strong base is going to conduct in a very strong way. So that's why the graph or the conductance is going to increase over here. Okay, so this increase is because of this strong base which is present. If we take weak acid and weak base, again since it is a weak base, so at the end instead of increase we will just get a flat line. This particular, in this case you get two endpoints. Okay, that is because first the conductance is like here your acid is neutralized, from here to here the salt which will be formed. For example, if you take a weak acid, let's say CH3 COOH, okay, and we are going to take a weak base. Weak base is, let's say, ammonium hydroxide. So what they are going to give you? They are going to give you CH3 COO and right, COO minus and CH3 COO minus and NH4 plus. Okay, and along with that you will get water. So basically from here to here, this particular part, this the salt, okay, the conjugate, not conjugate, the salt formed by this formed by the conjugate base and conjugate acid of weak acid and weak base respectively, it's going to conduct from here to here. And because these ions are not going to bind that strongly with each other, because they are formed from the conjugate base of weak acid and weak base, so they are going to conduct up to quite good extent. But at this particular point all of your salt is also, like, everything is neutralized over here. Okay, so the only thing which is left out is excess of weak base. So only excess of weak base is responsible for the conductance further. So that's why you are getting a flat line here. Okay, just like you are getting for this, for the weak base. So I hope this particular titration is much clear to you. Next, called as titration curves, or also called as pH curves. So here we also, like, here we plot your pH versus volume of acid or base added. So it's pretty simple to understand them. Okay, just look upon the graph very carefully. You are plotting pH versus, let's say, volume of acid. So if you are adding volume of acid, that means if you are adding acid to the solution, what was earlier in the solution? Earlier you were having base in the solution, right? So if you have base in the solution initially, so pH will be high. That's why you are having a higher pH value initially, and your value will keep on be higher only up till the end point, up till the point where that is called as equivalence point. Okay, so this is the point which is called as your equivalence point. So at equivalence point, what will happen, that all your base is going to get neutralized by the acid. Now if you keep on adding acid in the solution, so what you have now, you have excess of acid now. So acid will have lower pH, so that's why pH has decreased. See, the pH over here is around 13 or 14, and here the pH is around 1 or 2. So that's because you have added strong acid and strong base. Let's say we are taking strong acid and weak base. So weak base will not have higher pH, it will have lower pH. The pH is around like 9 or something. And then after reaching the equivalence point, the pH, the final pH, this is the initial pH. The final pH again came out around 1 or 2. That's because you have a strong acid in the solution. If you take weak acid and strong base will give you higher pH initially, right? So pH will be 13 or 14, and since you have weak acid, so its pH is not that much, so the final pH will get around 6 or 5 or 6. And if you take weak acid and weak base, so same thing will happen. Initial pH is going to be around like 8 or 9, and the final pH is going to be around 5. Okay, so like that. So this is how simple it is. Okay, pH curve. So you just have to analyze the curve and see it. Okay, the nature of the curve can also be different depending upon what you are adding in the solution. So if you are adding acid to the solution, you will get a curve like this. Okay, because initial pH is higher and final pH will be lower. But instead of that, if you will add base to the solution, okay, if you add base to the solution, so what will happen, you will consider that initially you have acid in the solution, then only base is going to titrate that. So if initially you have acid in the solution, so obviously the pH will be lower, and since you are adding the base again and again, so the final concentration will be there where you have only base, like you have more amount of base and less amount of acid. So more base, so that means pH will be high. So initially low, finally high. So this is where you are going to add base in the solution, and this is where you are adding acid to the solution. So these are the two different ways of titration, whether you are titrating acid with base or you are titrating base with acid. Okay, you have to be very careful with these terms and this graph. Okay, next thing is from your cell potential. Cell potential is calculated as E of cell is equals to E cathode minus E anode, or E right minus E left. How to find out this? There is a very basic term which you should know, that is called as LOAN. L for left. Okay, I'll write down here. So L for left. Okay, O for oxidation, A for anode. Okay, it's anode, and N for negative. So what does that mean? It means that in a cell, in the left hand side you have oxidation half cell, and that electrode in the oxidation half cell is called as anode. The charge on the anode is going to be negative. Okay, that's what it is. Okay, so E cathode minus E anode is how we write down. Gibbs free energy is calculated as delta G is equals to minus NFE, where N is the number of electrons which are given or taken during the cell reaction. F is your Faraday constant. F has a particular value of 96500. It's a rough standard value of it. E is the EMF of the cell. Now Nernst equation are there which tells you, or which relates your concentration with the EMF. So E of the cell is equals to E naught minus 0.059 upon N log concentration of, okay, this is for this reaction. If A and B reacts to give you C and D, where small a mole of A reacts with small b mole of B with small c mole of C and small d mole of D is what you are getting. So in that particular case, you have the like your Nernst equation is given like this, okay, E is equals to E naught minus 0.059 upon n log C to the power C d to the power d a to the power a b to the power b, or you can say that E is equals to E naught minus 0.059 upon n log reduction upon oxidation. So this is again called as your Nernst equation. Next is called as your Faraday law of first law of electrolysis. It says that the mass of the substance which is going to be deposited on the particular electrode during the chemical reaction or during the electrolysis, so that mass is going to be that is going to be proportional to the that mass is going to be proportional to the charge which is being transferred. All right, so that's what it is. So mass is going to be proportional to the charge which is being transferred to that electrode. Priyanka, the image is blurry, is it so? I think it's fine, only your internet, sorry, see, this is going live, right? So if you will not stream it in high resolution, image will be little blurry, okay, Priyanka? So you should stream it in the go to the settings and just maintain the quality to 480 pixel, minimum 480 pixel, okay? Then it will be fine. You will be able to read that. If it will be lower than 480 pixel, you won't be able to read the terms, okay? Fine. The next is your Faraday's second law of electrolysis. It says when the same quantity of electric current or electricity is passed through several electrodes, the mass deposited is proportional to their respective chemical equivalent or respective equivalent weights. Okay, so mass is proportional to equivalent weight. Okay, equivalent weight. How do you calculate equivalent weight? Anybody remembers that? So equivalent weight is calculated by this molecular mass divided by your X factor. Okay, what is X factor? You might have studied it in class 11th or 12th to calculate equivalent weight. So X factor for acid is the number of H plus ion, for base it's the number of OH minus ion, for salt it's the number of electrons which are used for your for that puja. Okay, which titration you want? I have already discussed the titrations, okay? Titrations we have done this. Which titration you want me to explain again? Conductometric or titration curve? Okay, at the end I will repeat that, okay Pooja? So let me just finish this, it's just about to get finished, and after that I'll repeat that, okay? You just let me know conductometric you want me to repeat or titration curve you want me to repeat. Okay, the next is your thermodynamic relationship between relationship between thermodynamic quantities and the EMF of cell. This is a very important equation. You should write it down somewhere because this is going to help you to solve many questions which relates thermodynamics with your EMF of the cell. So E of the cell is equals to minus delta H upon RT plus T del E of the cell by del T at constant P. Next is your ionic strength. Ionic strength tells you about that in a particular in a particular solution where your ions are responsible for the movement of charge. So what's the strength of that solution? Okay, so it just tells you that how much more electric current it is able to conduct or less. Like it just relates that. Okay, if you have two solutions, you can tell that which solution is going to be a better conductor than the other one. That's what ionic strength does basically. So ionic strength is denoted by I, and basically I is equals to sigma basically 1 by 2 and sigma Ci Zi square. That's how we do. Ci is the concentration or and Zi is your charge. Ci can be expressed in many terms. It can be expressed in molality, it can be expressed in normality, it can be expressed in molarity also. So it depends, okay? It depends upon different conditions that where you are expressing this Ci. So in all the ways you can just calculate the ionic strength, okay? So Ci is subjective. You can take it as molality also and molarity also. Mean activity coefficient is given by log gamma plus minus, and that is equals to minus a z plus z minus I to the power 1 by 2 or under root I. Okay, this you can also write down under root I. So this basically what does it means? It means that when you have a static charge in a solution, let's say I have certain charge particle, so there will be a counter ions which are going to surround this charge, okay? All around this charge they are going to be the counter ions which are going to surround. Then again, because these negative charges have come across, these charges comes from the dispersed phase, okay? Yeah, so it comes from your sorry, it comes from the dispersion medium. That means basically it comes from the solvent in which it is dissolved. Okay, this black colored charge is of the solute particle. Okay, this is the solute particle. The green colored ones comes from the solvent. Because of that negative charges, the positive charges of the solvent will also come and they are going to surround this. Okay, so what will happen, that the other charges are not going to come up till this length. So this is a certain length up to which this charged species or this charged ion is screened from the other thing which is happening in the solution. So in the solution you will have positive ions, negative ions, all those things, or some other charged particle would also be there. So that charged particle will not be able to influence it up till this distance, and that distance is called as Debye-Huckel length or Debye length. Okay, so Debye length is a length up to which a charged species in the solution is screened from the nearby or from the neighboring charges. That's what we call it. So Debye length is given by this formula lambda d, and you just have to see there are other terms which are over here, like you have, okay, I'll just write down here. So you have Debye length lambda d is equals to, it's like epsilon naught epsilon r kbt. All these are constant. Epsilon naught is permittivity of free space, epsilon r is relative permittivity, kb is Boltzmann constant, T is the temperature, divided by, you have 2 Na is Avogadro number, and E square is the charge of the electron, okay, multiplied by 1 upon I, okay, and whole to the power 1 by 2. So you have to see this, that Debye length is basically having all the other things constant except the temperature. If temperature is kept constant, that also remains constant. The only thing which is going to change is your is the ionic strength. So Debye length is inversely proportional to under root of ionic strength. Okay, so this is the relation by which you can do most of the questions which will be asked in your CSIR-NET exam. Okay, so this is the relation which you should know. Baki rest of the constant, if you don't know also, that will also work, but relationship you should know. Okay, ionic strength of the electrolytic solution is given by over here. I have again written the same formula. C is the concentration and Z is your charge. Alright. Now there are two types of cell, okay, concentration cells. What is concentration cell? The concentration cell is the one where the species in the oxidation half cell and reduction half cell is same. The only difference is that they have different activities both side. So those are called as concentration cells. So concentration cell can be with liquid junction potential or without liquid junction potential. Now what is with liquid junction and without liquid junction? So okay, so if you have a concentration cell, let's say like this, the cell is divided by this particular layer, okay, the concentrations are different or the activities are different, A1 and A2 here. So let's say the charges are able to move from A2 to A1 very easily, okay. So what will happen when the charges will move, they are going to form, okay, the counter ions are going to form a layer around this junction, okay, around this junction you will have a layer form. This is called, and because of that layer a very small amount of potential is going to created, because those are going to be opposite charges, right. It's pretty simple. If you don't want, if you didn't understood, I'll just explain it once again. So let's say that in this concentration cell the positive ions are your charge carriers, okay. Let's say the positive ions are your charged carriers. So this is the concentration cell. I told you the concentration cell has same thing on both the sides. The only difference is with the concentration or with the activities. Let's say this is A1 and this is A2. The charge carriers are positive ions. What will happen, that positive ions are going to jump from here to here, okay, from this side to this side, because let's say A2 is greater than A1. So your charged carriers are going to move from this to this side. So what will happen, after some time on this side a more amount of positive charges are going to they are going to come and they are going to generate, or they are going to stay near this junction, okay. More positive ions are going to get stayed over there. Now because more positive ions are here, so obviously to balance those charges or to counter those charges, negative ions will come and they are going to come at this particular junction. Now they are not able to, they cannot jump from here to here from the junction. Why? Because of the higher or the difference in the activities. They will just stay like that. And because positive ion and negative ion both are staying near to each other, so they are going to develop a potential, and that potential is called as liquid junction potential, okay. So liquid junction potential is this. and the formula for this is given by like minus 2t minus RT upon F and ln A1 upon A2. Okay, A1 and A2 are different activities of the same concentration cell, and for spontaneity you should know that A2 should be greater than A1. This is for the spontaneous process or for the spontaneous reaction. Now this liquid junction can be removed. You can remove this liquid junction very easily if you just put a salt bridge here. Okay, if you just put a salt bridge, that salt bridge is going to neutralize this these like junctions, sorry, the charges at the junction, and that's how it will be. So E with liquid, without liquid junction potential is going to be minus RT upon F ln A1 upon A2. The same thing is there, the only difference is that you don't have this 2T minus, so the transport number is gone, because now the ions are not going to play much role over here, because the ions have been neutralized by this salt bridge. Okay, so that's what the difference between liquid with liquid junction and without liquid junction. Alright, so Pooja was asking to explain titration curve. I am just going to explain titration curve once again. Okay, titration curve, basically in that you have pH versus volume. Okay, volume of what you are adding. So let's say I am adding acid to the solution. Acid means initially I am having base in the solution. Okay, the solution only has base, so its pH will be high. So I have higher value of pH initially. Now if I keep on adding acid, what will happen, that at a certain concentration of acid all the base is going to get neutralized. So that concentration of acid is what is called as the equivalence point or the end point. So the equivalence point will be the concentration of acid at which all the base is going to neutralize, and if this base is getting neutralized, so then if you keep on increasing the concentration of acid, what will happen, that only acid will be present in the solution, and only acid will be present, so its pH will be lower. So initially high pH and then lower pH. Okay, I have discussed this over here itself. Fugacity concept is important. Yes, Kirtana, fugacity is important. Fugacity is nothing difficult in that. Fugacity is basically how we express pressure for the real gas terms, okay, or for the real gas system. So in the ideal gas system we express pressure in the terms of pressure only, but when you come for the real gas system, there we express pressure in terms of fugacity. Now fugacity, yeah, and also you should know that this term fugacity came from the chemical potential. When you have studied that chemical potential in thermodynamics, chemical potential is basically a property which changes with the flow of or with the movement of number of ions, which depends upon number of ions. So it basically talks about the open system. So if you have an open system of a real gas, their fugacity comes. So wherever you have pressure, you can change that with the fugacity term. Okay, let's take some questions, very simply and very easily we'll try to see. We'll take 3-4 questions and we'll end up the class. So it says a specific conductance of electrolytic solution is this much, and the cell constant is this much, conductance of the solution is. So you have a specific conductance, so you are given with the kappa value, or you can say that you have conductance value. Okay, you have conductance, it's 0.2 ohm inverse centimeter inverse, and you are given with cell constant. So remember the first formula, I have discussed the first formula for this, and that formula is going to be used. Okay, so specific conductivity is equals to conductance into cell constant. That's the formula which we'll use. So conductance, okay, into cell constant. Specific conductance it is given, sorry, specific conductance it is given, not conductance. Specific conductance is also called as conductivity. Okay, conductivity and specific conductance is same. So basically this is not conductance, this is conductivity given. Okay, conductivity. So remember the relation, what's the relation is? Relation is that conductivity is equals to conductivity is equals to conductance into cell constant. Just put the values. Conductivity is 0.2, conductance we don't know, cell constant is 0.25, so G will be equal to 0.2 divided by 0.25. Solve this and you will get the answer. Okay, I guess option 3 will be the correct one. Yeah. Okay, option 3 is the correct one for this. All right, again the same question, same concept. Okay, June 2017, same formula you have to use. So I'll leave this question for you. Okay, I'm just staying on this question. You can take screenshot and try to solve this. Okay, just try to solve and see what's the answer for this. Okay. Alright, the next one says electrochemical cell potential after reactant and product reach equilibrium. So what will happen to the reaction when what will happen to the Nernst equation when the reaction reaches to the equilibrium? So remember that at equilibrium your E of cell is equals to 0. Okay, your E of the cell is 0, not E naught. Okay, remember this. So E of the cell will be 0. So option number 4th is your correct option. Okay, equivalent conductance at infinite dilution and strong electrolyte can be obtained from the plot of, this is asked from your Kohl-Rosch law. Okay, Kohl-Rosch law. I have already discussed in the class. I'll leave this for you. Okay, just try this and see which is the correct one. Okay, I'll tell you the answer is option number 2. Okay, but see how the Kohl-Rosch law is related to it. Okay, this question is says titration curve if a strong base is titrated with a strong acid. Strong base and you are adding a strong acid. So see, you are adding volume of acid in it. So what should happen when you add strong acid? The final pH should be low, right? Yeah. So final pH, volume of acid, sorry, yeah, volume of acid is being added. So initially what you have base. So base ka pH, what will happen to the pH of base? It should be high, right? So pH of base should be more, yeah. And here if you see, the final pH should be less because you are adding acid. Okay, so option number C is the correct one for this question. Okay. Alright, this was a question from your GATE actually. This was asked in GATE 2016. It says titration of a strong acid with a strong base represented by the plot. Now you have to be very careful that you are adding a strong acid with a strong base, but you are doing that, you are plotting that. Okay, so but remember that what you are putting or what you are plotting on the x and y axis. So on the y axis you are plotting delta pH by delta V. Okay, you are plotting delta pH uh, delta pH by delta V. That's what you are plotting. So you have to be very careful with it now. Delta pH means change in your pH values. Okay, so what's the change in pH happening? You are adding strong acid with a strong base, so it has to be the curve. The general curve which we have studied has to be something like this. Okay, because you are adding a strong base, so base is what you are adding here. Okay, base concentration is what you are adding and pH versus this. Now check this out. Initially is there any change in pH? Delta pH, what about the delta pH? Is it any change in that? So no, there is no change in that, right? So your delta pH is, sorry, delta pH from here to here, I'll just mention points. Okay, from A to B, from B to, let's say this is the point C and this is the point D. Okay, so from A to B, what will happen? That delta pH is 0. There is no change in pH, you can see. From B to C, what will happen? That your delta pH has increased. Okay, your delta pH has increased from B to C. See, the change in pH is quite more. The pH was low and then it became very high. So the delta pH is high here. Okay, and what will happen from C to D again? So from C to D again, your delta pH will be equal to 0 because there is no change in pH again. So the graph should be, if you are plotting delta pH was divided by delta V, if you divide it by delta V also, that is not going to make any difference. But yeah, if you plot it, so what should happen? That initially it should be low, then it should become very high, then again it should become 0. So like this, the curve should be like this, which is mentioned here in option number C. Okay, so this is the correct option for this titration. It was a very good question asked in GATE exam. Alright, so before going for the next question, okay, before going into the next one, I would like to tell you regarding the revised India program. Okay, alright, so before going any further, I would like to inform you regarding the revised India program, which is running on Unacademy platform. And like all the educators are taking revision classes over there. So today, that is on 15th of November, I am going to have a class at 7 p.m. Okay, at 7 p.m. I am going to have a class on quantum chemistry. So if you are interested, you can join my class on Unacademy platform. ठीक है? हाँ साम्रा, आज Unacademy पे class है. This is a free class which I am going to conduct at 7 p.m. today. Okay, so time is 7 p.m. It is very absurd time which I don't used to take class, but today I am taking at 7 p.m. Okay, so please, if you are interested, you can join the class. The link of the class and other things you will get in the comments of this particular video. Like I would just point out my comment from my channel, so you can just click on that link to like join the class. Or the other way of joining the class is just by going to my channel. Okay, my channel is there, that is, its name is All About Chemistry. So you can go to that channel and you can get the link, like access to the link. Okay, so that's how you can join the classes. Alright, so yeah, so this Revise India program is running up till, it will run up till the CSIR-NET exam. So take the best of it, join the classes and keep revising the topics. Alright, let's take some more questions. Let's take some good questions now. Okay, the question over here says the predicted electromotive force of the electrochemical cell. The cell is given to you, Fe, and then you have Fe plus 2, and the concentrations are given to you, and the cadmium. Okay, so you have two electrodes, iron electrode and cadmium electrode. The reduction potentials are given to you. If you see, so your iron is getting oxidized, and if you see, the cadmium is getting reduced. Okay, so how it will done? Iron is getting oxidation and cadmium is getting reduction. So you know that E naught of the cell is equal to E reduction minus E oxidation, or E right minus E left, or E cathode minus E anode. So if you put the values should be in the reduction potential only. So reduction potential of cathode is written minus reduction potential of iron is written. Just calculate that and you will get 0.044. So the answer is option number 2. Okay, that's how it will be done. Okay, the next question is very simple one. Standard cell potential of the reaction is given to you. Gibbs free energy is being asked. So you know delta G is equals to minus NFE. Just put the values and just calculate it. It will give you the Gibbs free energy. Okay, so this particular, okay, next are gate questions that I am not going to take. I'll be taking that in the courses which will be launched for the gate exam. Okay, one more thing, that those who want to join my live classes, okay, if you want to join my live classes on Unacademy, okay, in that case you can join that. New batch is going to start from 30th of November. Okay, 30th November 2020, new batch is going to start for CSIR-NET, and GATE batch is also going to start. So 2-month course is going to start for GATE exam. That's going to be a revision course. So if you are interested, you can join the Unacademy classes. Alright, so I guess that's all for today's class. That's all I'll be taking for today. I'll see you guys next Sunday with the next topic. Till then, have a great day, and just keep preparing for the exam. Okay, all the best for your exam. Alright guys, bye bye.